Hi everyone, this is video 1.2.1 on Beer's Law first. The whole thing is on solution analysis. So today we're going to be talking about Beer's Law, a little bit of what happens when things dissolve in solutions, and just more of a molecular view of those solutions, so what's actually happening in there. So we're going to start off by looking at Beer's Law, and the first thing we're going to look at is colorimetry. So colorimetry really is a lab technique that's used to determine concentration, but it can only be used to determine the concentration of solutions that have a color to them. So things that are clear we're not going to be able to use colorimetry because really we're looking at the intensity of the color. Okay, so the purpose is to determine the concentration of colored solutions. Always colored solutions. You can't use it on colorless ones. You can't use it on clear solutions. Okay. Knowing that now, you should be able to figure out the answer to number 2. So please pause the video and go ahead and circle just the compounds very quickly with which colorimetry would be useful, when we could use it. Okay, we're back. So aluminum chloride is a colorless solution. We would not be able to use colorimetry with it. Colorless, can't use it with calcium chloride. However, cobalt chloride is pink, and we could use it with cobalt chloride because it's pink. Anything with a color, so we can use it here, here. This is going to be yellow. So there, purple. We can use that. Colorless, nope. We can't use this to figure out how much salt is in a solution. Green, nickel chloride, really pretty solution. No, we can't use it on zinc chloride. So basically anything with a color. Okay, so what is Beer's Law exactly? So Beer's Law is a very useful formula that we can use. So our big A is going to be absorbance, and that's going to be dependent on some wavelength, lambda, and that's going to be equal to lowercase a times B times C. Okay, so let's list these variables out. So this depends on your wavelength. So this symbol, this is the wavelength of light used. Wavelength of light used. A is the absorptivity constant, and this is going to be different for every solution that you're going to use. It's some absorptivity constant, and it has to be determined experimentally. Absorptivity constant. B is the path length, so that's the distance that the light is going to travel through the solution, and it's usually 1 centimeter when you're using a standard colorimeter. So path length, usually 1 centimeter. We'll go ahead and write that here. And C is our concentration of solution, which is usually what we're the most interested in. Concentration of solution. Okay, so what factors affect the absorbance of the solution? Well, that's going to be A, B, and C. We already kind of listed that here. But when A increases, when the absorptivity increases, or sorry, the absorptivity constant increases, the path length gets longer, or the concentration of solution goes up, the absorbance is also going to increase. So when A, B, or C increases, A, B, or C increases, the solution absorbs more of the light. That is, the absorbance is going to go up. And if we think about that, that makes sense, because the darker and deeper the color is, the more light is going to be absorbed, the less is going to get through, or what we would say is transmitted. Okay, number 4. How do we determine what wavelength is ideal to use? Well, what you do is you look at how light is absorbed over the whole spectrum of visible light. And then you use the wavelength at which the absorbance is the greatest. So we're going to write that down, and I'll show you a graph of what I mean by that in just a second. So look at how light is absorbed. Over all wavelengths of visible light. And then choose the wavelength at which the absorbance is greatest. Okay, so let's take a look at a graph. Number 5, the absorbance spectrum of a sample of crystal violet and an absorbance versus concentration graph are shown below. We're going to take a look at this one first. This is the absorbances. These are all the absorbances of crystal violet at each of these particular wavelengths. So we can see that if we shine some light at 350 nanometers or 400 nanometers on it, it's not going to absorb so well. However, once we get to closer to the 550, 600 range, the absorbance really skyrockets. So we're going to want to choose, if we were to analyze crystal violet, we're going to choose a wavelength of, let's say, about 600 nanometers. So it absorbs highest, absorbs most at 600 nanometers, at about 600 nanometers. Okay, and so our next graph then, we're going to say this is absorbance versus concentration at 600 nanometers. So the next graph is going to be assuming that we actually carried out the experiment, and this is the graph. This is our output that we got. So this absorbance is on the side, so same as up here. Our absorbance is unitless. And here's our concentration in moles per liter, which is molarity. So note that this is times 10 to the negative 6, so these are very small numbers. That's not 10 molar. That's 10 times 10 to the negative 6 molar here. Okay, so let's look at these questions. Approximately which wavelength would be optimally used for the colorimetry experiment? Well, we determined that up here because it absorbs most strongly at about 600 nanometers. We're going to use 600 nanometers. So we're going to use 600 nanometers. Okay, what is the molar absorptivity of crystal violet at that wavelength? So the molar absorptivity is the absorptivity constant. So that's going to be this A. So what we're going to need to do is use Beer's law that we wrote right here, and we're going to need to solve for this A. So I like to rearrange my equations before I get started, before I plug anything in, so I'm just going to do that. So rearranging, I get my absorptivity constant is equal to my absorbance over path length times concentration. And to solve this, we're going to choose any point on our graph above. So choose any point on absorbance graph. And here we're going to assume our path length is 1. So B equals 1 centimeter. Okay, at this point, I would like you to choose a point, any point from this graph, and I would like you to pause the video, and I want you to plug that in and see if you can solve for the absorptivity constant. Okay, so I'm going to go ahead and choose a point. I'm just going to choose this point right here. I just like that point. So you can choose any point. It didn't have to be this point. You could have chosen any of these. So I'm going to go ahead and plug in my data from my points. So my absorptivity constant is going to be equal to my absorbance A. My absorbance A I get from reading this graph. So my point is about 3.9. So I'm going to put 3.9 for my absorbance times B. So B is our path length. That's going to be 1 centimeter. And my concentration. So my concentration is 12 times 10 to the negative 6 moles per liter. So times 12 times 10 to the negative 6 moles per liter. Now, another way to write per liter instead of using a fraction is just by using this inverse notation. So this moles per liter is the same thing as me writing, moles per inverse liter. That's the same thing as me writing moles over liters. This is the same exact notation. You can write it like this to keep it neater and in line. It's up to you. Okay, when I plug all of this into my calculator, I end up getting a value of 3.3 times 10 to the 5th. And my units here are interesting. Liters times inverse moles times inverse centimeters. So this would be the exact same thing as saying liters per mole per centimeter. So instead of me writing liters over moles times centimeters, I can write it like this. Okay, so here is our A, our lowercase a, our absorptivity constant. And now that we have that constant for crystal violet in this experiment, we can go ahead and use that to figure out the crystal violet concentration of a solution with a different absorbance. So we're going to go ahead and do that now. So given that the absorbance is 0.050, what is the concentration? So again, I'm going to use my Beer's law, and I'm going to need to solve for C, my concentration. So rearranging first, I get my concentration is equal to the absorbance over our absorptivity constant times our path length. And we're going to use A from problem above. We're going to use the A we already solved for because this is the same substance, and this is the same experiment here. Okay, so plugging everything in, my absorbance was given to me, 0.050, divided by A, which I solved for up here, 3.3 times 10 to the 5th liters times inverse moles times inverse centimeters times B, our path length of 1 centimeter. Our units here cancel out. Inverse centimeters and centimeters cancel. They're right next to each other. This is the same as 1 over centimeters, remember? And this is just centimeters, so those would cancel. And the units I'm going to be left with is liters over liters per mole. But this is on the bottom of the fraction bar, so really it'll be flipped and be moles per liter. So our concentration, when you plug all of this into your calculator, should be 1.5 times 10 to the negative 7 moles per liter. So go ahead and plug that in. Make sure you get the correct answer there. Make sure you understand how to utilize Beer's law. That is the end of video 1.2.1. See you next time.